I'd like to thank the organizers for the invitation. It's an honor to speak here. As my collaborators can attest to, I've been looking forward to this for weeks, and it's living up to all my expectations. So, okay, today I'm going to be talking about joint work with Adrien Abgrall. I'll start with reminding us of some definitions. So, a group G is residually finite if anytime you take some non-trivial element, there exists a quotient to a finite group such that the element you fixed survives. And we'll take a topological perspective in this talk. So here's an equivalent definition. So letting X be, say, a complex, CW complex, with fundamental group G. G is residually finite if and only if. So for all essential closed paths, I can find a finite index cover. So this will be a finite index cover. Such that the lift of P I'll put it here. Is not closed. Okay. So I'll describe this as saying just orally as X hat opens P. So I'm going to give some proofs of probably some well-known facts to the audience, but the proofs will be sort of emblematic of the type of arguments we're going to make for the main theorem. So here's the first thing, which is a group, well, let's say a free product of residually finite groups is residually finite. So, right, taking the topological perspective, I'll realize A and B as the fundamental groups of two complexes, and I'll write G as the fundamental group of the complex corresponding to A, and I'll just add two edges and join it to the complex corresponding to B. And now a non-trivial element, so I'll fix, since it's a free product, I can rewrite it in something in the form A1, B1 through AN, BN, and I'll just assume for the sake of argument that A1's non-trivial and BN's non-trivial, but if they are, you can fiddle around and it still works out fine. So fixing this, I'll pick covers finite degree, XA, so opening the elements of A and B that appear inside of G. Right, and now the game is to show that I can build a cover so that G lifts to some non-closed path. So maybe I'll go over here. So here's xa hat, and suppose, for the sake of this cartoon, it's degree 3. Well, I know that A1 opens, so it ends up on some different open edge than the one I began on. And then to this, I can attach a cover XB that I've picked, which I'll make degree 2. All right. This is B1. And because I picked XB so that B1 opens, I don't end up back here, and so on and so forth. Until I've completely opened up G. So this will be AN, and this will be BN. Right. And then this is a partial cover, so but you can convince yourself that, well, you wire shut closed the sort of open ends of XA and XB as much as you can, and up to adding some more copies of XA and XB, you can close everything up. And then at that point, you've constructed a finite cover that opens G. So big G is residually finite. Any questions about that proof? OK. So the groups of interest to us, let's maybe put it over here. I'll say G splits as a graph. 3 groups. So I'm going to realize them as the fundamental groups of some graph of spaces. If G is pi1 of a graph of spaces with graph vertices and circle edges. So the cartoon to have in mind is something like the following. And I can write each attaching map here as some W to some power. So I'll draw a few more. And I'll make the convention that each Wi is an immersed cycle. That's not a proper power. So, if your attaching maps weren't immersed to begin with, you can tighten them, and then if they were some proper power of a cycle, you write Wi the root, and then take the power that you need. So examples, well, they include free groups. They include surface groups. I guess here I mean a surface that you have a Pants decomposition for. and that's how you realize them as such a graph of groups. And Baumslag-Solitar groups. So these will be important for the talk, and they're defined by presentations of the form AT, where T conjugates A to the P power to A to the Q. And we can make the convention up to swapping A and T for their inverses, that we'll take P to be positive, and the absolute value of Q will be at least P. Okay, what do I want to say about these? So we're going to be interested in separability properties. So this is lerf if and only if P and Q are equal to absolute value, and it's residually finite if and only if either it's lerf or P is equal to 1. Okay. Questions? Great. Okay, so sort of motivated by those 2 bullet points, for any group G, an infinite order element we'll call it unbalanced for some H and G. If H conjugates some power of G, where those are distinct. And we'll call it very unbalanced where now I ask that 1, P, and Q are distinct. And so this is some sort of minimality assumption. So if, let's say, where is it, P, if Q were to divide P, that should imply that HG, Q divides P, yeah, P divides, should not be equal to G. You can't simplify that way. And if the reverse, so if P were to divide Q, that should imply that HG okay, and I mean the reason for that is because in BS1-2, say, so I'll just say, how should I do this? So TA T squared inverse equals A to the 4 in BS1-2. So you might think, it's very unbalanced, but you've cheated because really this was implied by a simpler relation where you reduced dividing the exponents by 2. So very unbalanced should mean you've really discovered something that looks a lot like one of these P equals 1 relations inside your group. Okay. Right. Okay, so maybe I'll start with something that's known. it's a theorem of Wise from 2000 that for G, with cyclic edges, the following things are equivalent. So G is lerf. Sorry? No. Lerf is subgroup separable. It's a stronger property than residual finiteness. Essentially, it means that there's a quotient separating any element outside of your favorite finally generated subgroup. Okay. Right. This is lerf. Okay. If and only if G contains no unbalanced elements. And maybe I should note here, so note that in general, the existence of unbalanced elements in a group, they obstruct lerfness. And this is an observation of Wise in this same work. So, I guess, yeah, he proved that for such groups, splitting as graphs of free groups and cyclic edge groups, in fact, that's the only obstruction. Okay, and then the theorem of Levit. I mean, you play games with the orders of elements in the quotient. It's a load of like LCMs and GCDs. Okay. Right. So this is for groups. I'll say, well, for a GBS group. So I'll just say what that is. That's a group splitting as a graph of, or as a graph of groups where everything's cyclic. So cyclic vertices, cyclic edges. We have that G is residually finite. If and only if. So he didn't say it in these words, but no very unbalanced elements. And also showed that this is same as no non-residually, or all Baumslag-Solitar subgroups are residually finite. So the existence of some non-residually finite subgroup obstructs residual finiteness, passes to subgroups. So in this case, as long as you don't have bad Baumslag-Solitar subgroups, you end up being residually finite. I could have tacked on another equivalence here, the corresponding thing.
And do you mean about Solitar that you see from the graph of groups, or
all Baumslag-Solitar subgroups are residually finite?
No, I mean like there. Do you mean it's enough that the one you see from the graph of groups are
yes, but finite? There's proof there. Yeah. So right, but maybe but the thing to be aware of is, in general, this won't, having non-residually or finding very unbalanced elements won't restrict or obstruct residual finiteness. So the example is, if I take Z adjoin 1/6, semi-direct Z, where the action is multiplication by 3/2, then this is a linear group, but 1/6 is very unbalanced. Okay, so something to be aware of. But nonetheless, for graphs of free groups of cyclic edge groups, Adrien and I have the following. So for G, we have that G is residually finite if and only if no very unbalanced. If and only if all Baumslag-Solitar subgroups. Okay. And maybe I'll say just a word about this, because that's basically due to Leavitt. So right. The worry is that, you might find some infinite order element that looks like it satisfies some BS1n relation, yet somehow you're residually finite. For a graph of free groups, you have the following argument. So you look at the action on the Basse-Serre tree, and you get that your G and H, which witness the very unbalancedness, belong to a GBS subgroup of G. And then Leavitt, in the work in 2015, tells us that very unbalanced and unbalanced in a GBS can be used to produce what I'll call very unbalanced or unbalanced Baumslag-Solitar subgroups. So you actually find an embedding of a subgroup, and you might actually have to change the parameters. So you might think you find like some 1n, but you have to multiply with some prime. Okay. Any questions?
What's start?
Group. Okay, well, I'll go Donnie first. Okay. GBS is a group splitting as a graph of groups with cyclic Z vertices, Z edges. Sorry, I said cyclic, I meant Z. Okay. Okay, so let's do a step up from this emblematic argument. Let's prove that. Oh, I thought you said I didn't have to answer that.
No, I said it was Kjot's question because he asked right at the beginning. You didn't answer it.
You can separate. I did. You can separate a finitely generated subgroup and an element not in it in a finite quotient.
Kasha says I should be nice. Fine, go on.
Okay. Let's say BS1Q is which is finite. Okay, so we realize BS1Q again as a fundamental group of some complex. So here A will correspond to the path that wraps around some loop. And we'll have a tube where one side attaches just by A and the other side attaches by A to the Q. And then we'll define some parameterized family of covering spaces. So do I want MN or? So this will be a covering space where I first take an n-fold cover of A. And then I'll take m copies of them. So there's going to be tubes here. Where this, let's give this a name. So that will be T, and this will be T to the M. So to make this a covering, you should ask that M and Q are coprime. And that guarantees that each edge here receives one incoming T letter, where these are A to the MQ. And over here is A to the M. Oh, and Q. Okay, and now I'll fix an element which will have the form and I want to show that some choice of n and m will open any such G. So maybe the easier case is if the exponent sum of t is not equal to 0, then I can pick some cover x and m that opens G for large M. Right? And the point is just that if M were large enough, then you would walk around the circle and eventually find yourself not back to this circle, so impossible to close. And if it so happens that the exponent sum was 0, well, then in fact, you can rewrite this as a product of conjugates of A, T conjugates of A, where the T's have powers, and deduce that G is conjugate to some power of A. So I'll just write A to the L for some L. And then so x and m opens G as long as n is sufficiently large. Because it suffices to open a conjugate, and if this circle is large enough, then A to the L won't close up. Okay. Any questions about that? So this is just a degree 1 cover labeled by A to the N, because that's A to the N. Here is a degree Q cover, A to the NQ. And yeah, that this is a covering space relies on M being coprime to Q. Anything else? Yeah, sorry, I don't have a citation. It's someone proved this in the 70s. Is it Moldovansky? No one knows? Okay. Okay, let's deal with a real example. So I'll let G be the following group. will be a to the n, say, and s will conjugate b to the n. Okay, so, I mean, this is a group in our class of interest. It's a single vertex with two edge groups where the free group is generated by A and B. And these are the T and S are the stable letters that give you tubes. So maybe the interesting behavior here is that any lift of T inverse AT, S inverse BS lands in the same vertex space. Sorry, any lift of this, say, has endpoints. In the same vertex space of any finite degree cover. So you need something to separate these, and here's where cubes kick in. So I'm calling it a theorem, but really it's a corollary of deep work of aix-1 y's. So y's and O4 cubulated C'16 groups, and Abel proved that cubulated hyperbolic groups are virtually special. So as a corollary, we get that pi1x is residually finite for x, a C'16 2 complex. And there's a nice upshot of that. So the upshot is, for our graph of groups, if we have distinct Wi and Wj, where these are the sort of roots of the attaching maps, these are distinct. And right, I'm emphasizing distinct because it is possible that, say, W2 equals W1. So it's not just that I and j are distinct. I want these to really be distinct cycles. So if Wi and Wj are distinct, then for all sufficiently large, say Nm, there's some finite degree cover so that the lifts lift to cycles labeled by Wi to the n and Wj to the m. Okay, and so if we're concentrated on this example here, and we want to open that word, then, well, this will imply that there exists the cover let's say AB, so that the endpoints of this first subword T inverse AT. And also independently S inverse BS. Are far apart, maybe I should say. So the cartoon is something like this maybe, where I have Wi to the n. I mean, here Wi is really just A, and Wj will be B, but more generally Wi. Wj to the m. And when I lift T inverse AT, what I'll see is my path will go up the tube, walk around a bit, and come back down. And then it'll do it again for this tube here. And when I say that the endpoints are far apart, what I mean is if I look at where I begin and end for S, is it? No, T inverse AT, this distance, call it K1, and this distance between the points, K2, are both large, arbitrarily large. And now, okay, sort of standard small cancellation theory. Will imply that the entire thing opens. So T inverse AT, S inverse BS opens. And, well, okay, maybe if you're not, small cancellation really gives you some sort of negative curvature, and you can view this as saying that you have something which is locally quasi-geodesic, therefore globally quasi-geodesic. So this opens. And then, with some care, then one completes to a finite degree cover. Where, again, the game is taking copies of this vertex space and sort of wiring up the open ends of tubes. Okay. Any questions about that? Okay, well, I'll give the sketch of the general argument now. So, for one thing, to build the covers, like in the, did I erase it? The BS1Q case, I needed to be able to pick M coprime and wire things up nicely, which will just be impossible if it was a non-residually finite one. So, okay. I'll define a graph, gamma. So here G is one of our groups of interest. So the vertex set is going to be the various Wi, which you can think of as being, the roots of attaching maps. And the edges, so I'll add an edge of this form. So joining wi to wj, and I'll label them, I'll label the ends of the edge. So here's ni and nj for each edge in my graph of spaces that looks like this. And having no very unbalanced elements will imply that components of gamma have the following form. So maybe I'll just draw some examples. So one thing you could do is, let me put you could have something like this, which, if I've done it correctly, if you draw any cycle, any closed cycle on this graph, and you multiply all the numbers you see on sort of the far ends of the edges as you visit them, you should get something equal in absolute value to what you get multiplying all the close ends of the edges. And that's one component you can get, or you can get components that look like this, where you have 1 and then some integer, some other integer, etc. And then maybe you have some trees hanging off of a cycle where the far ends are all labeled with 1. And then, okay. So it's some labeled graph, or graph with ends of edges labeled, and either you have something where these two multiplications for any cycle are equal in absolute value, or you get components of this form. And this just follows from the fact that if you had something more complicated than either of these, you could sort of read off a very unbalanced element. Yes?
Because it looks like I can interpret your graph as vertex groups are cyclic and edge groups are just like finite index graphs.
Yes, so there's some work to check that something that you read off would embed, and that would use Levy. Okay, so here's the sketch. So fix the element you want to open. There will be a decomposition with such that each SI behaves a bit like one of these words. Okay, so I guess I'll end there because my time's over.